Yeah, so my name is Alexei Orlov. I'm presenting a team for University of Notre Dame, which is located close to Chicago. And so this is we did it with most of the work was done by my grad student Istiaque, and we are doing also measurements together. So first of all, so the title of the talk, as you can see, it's related to dipole charge detection, and this will be a very different scale compared to embroidery, for sure. So we're talking about nanoscale this time around. And I guess I need to introduce you to the concept of quantum dot cellular automata, which was devised well some years ago. Okay, anyway, so this group of people, these are theorists from our department, they came up with this Notre Dame architecture. So the idea is, instead of encoding binary information and voltages and current levels, why not use spatial position of, for example, charges, and then use these charges, like in this case, that's what is called cell, quantum dot cell. We have 4 quantum dots. They put 2 electrons there, and then do Coulombic repulsion like that. And then you use them as the Lego blocks. So the cool part about that, if you place these cells close to one another, due to Coulombic repulsion, they tend to align in a specific way. So, like if you force it to sit like that, next cell will align accordingly. And this is a bistable nonlinear cell response, which ensures the signal level restoration once you put this together. Okay, so now using this Lego blocks, what you can do, you can build majority gate. The majority gate gives you all these Boolean functions that you need to either get or AND gate. And then you can connect these things together using so-called binary wires. They have just a bunch of cells aligned. So if you switch one, they will flip like the dominoes. And there's an example of 2 letters of QCA. So basically, you combine this letter units and perform certain Boolean functions. Now, the funny thing is exactly 25 years ago, because this paper was published in November 1st, 1998. We published this paper where we demonstrated the cell operating at 70 millikelvin using aluminum junction technology. Basically, it's basic cell. You can see the scale of things with 1 micron. But of course, it's not really a great idea for technology to operate at 70 millikelvin. It's a little difficult and need to be obviously lots of cells. So naturally, if you come to think about what can be used as Lego units, you can think about molecules. You can find some molecular compounds where you use oxidation and reduction reactions to essentially create this switching of electrons in there. Well, why molecules? Well, of course, they're small and they're uniform, and then you can create huge densities of them, so you can create complicated circuits. And important thing is that it allows for room temperature operation, because in order for these things to work, you need to beat the thermal fluctuations. And the characteristic energy is so-called charging energy, which is related to the capacitance of such a structure. So if your charging energy is greater than kT, you can do some useful things with it. And for 1 nanometer size object, it's pretty easy to operate at room temperature. Okay, well, but if let's say you can build such a structure, how do you measure it? How do you measure the output of that? And basically, that's where we come to the point of my talk, which is basically detection of the dipoles, right? So if you have 2 dots, let's call them dots for simplicity, which are separated by some tunnel barriers, so we can go back and forth. So you need to detect this dipole, where the charge is located, okay? So if you bring a sensor, okay, if you just bring it like that, and you couple equally to both of them, of course, there's no signal, because they'll be just killing each other, right? So the voltage generated by this charge switching is proportional to the characteristic charge energy, where the C sub sigma is the capacitance of such an object. Okay, so like I said, if they're coupled equally, there's no signal. But if you place your sensor differently, create some asymmetry, then you have some delta C, which enables your detection. If you make it closer and a little bit more asymmetrically, you get more signal, right? Okay, so now what kind of sensor we can use? Well, one in principle can use field effect transistors, but they're very inefficient compared to single-electron transistors, which have the best electrometers available on Earth. And you can achieve sensitivities down to 1 microelectron per square root hertz, meaning that you can resolve very small increments of charge. And now let me switch gears and talk a little bit about our fabrication process. That's how we make these devices. And we use high-resolution e-beam lithography and so-called, this is so-called Niemeyer-Dolan bridge technique. So it's a high-resolution e-beam lithography plus shadow operation through the stencil mask. So this is reverse evaporation of aluminum. Then we do oxidation in situ at low pressure. So we create tunnel transparent dielectric about 1 nanometer thick on the top of this aluminum. Then we do shadow operation at a different angle. So it creates the wires are going through here. So the junctions here, a gate. And that forms this device, which is called single-electron transistor. And if you sweep the gate voltage, you will end up with such a characteristic response, which is known as a Coulomb blockade oscillations at low temperatures. Again, you need to be careful with temperatures. You need to make sure the junction capacitances are pretty small to be able to operate it. And you see this is like the distance between the peaks is exactly 1 electron. So you can see, since they're pretty steep peaks, you can resolve the charge increments, which are far smaller than 1 electron. And now let's go back to our dipoles. We fabricate this little toy experiment with large-scale dipoles. So we can see they're about one micron size in length. And if you apply bias, if you apply plus here, you push an electron here, and you create a vacancy on the other dot. You switch it, you do the opposite. And if you measure the results with 2 electrons, you can here, use 1 electron in this case, and we see that, so the blue curve is the response of the electrometer. The red curve is the response of this differential bias. So just put on the same scale to be able to explain what's going on. So we basically jumping from one working point to the other working point. So it corresponds to a small change in delta Q perceived by this single-electron transistor. And so we basically, let's say we sit around 0, we apply some bias, so we put 1 electron to go this direction, we'll be getting more and more electrons to here, removing more electrons from the other one. And it gives you this characteristic sawtooth function, which you observe as a red curve. Well, how we can scale it towards molecules? That's a good question, right? So we can, since we have a very high resolution e-beam lithography machine, we can scale it down. This is a fun slide because this is what we literally did. This is the same, that's to scale. So we went down from a couple of microns down to tens of nanometers. Let's zoom in on that same device. So we can see this is our little dipole. It's a false color. Nothing is green there. But this gives you an idea. This is one detector. It's another detector. That's your dipole. And these are the gates which they push electrons back and forth. So again, this is just a representation of the same thing. Just what happens with these two operations. So we create a dipole and we create this parasitic dots, if you wish, but it's a byproduct of fabrication. But they kind of act as a field enhancer, couple this specific device more to this dot, this specific device more to this dot. And from the standpoint of like circuit diagram, that's kind of a messy picture, but that's what happens really because you have everything coupled to everything else. And just as far as this dimension, so the size of the first island is slightly bigger because it's the first evaporation. During the second evaporation, the opening is partially clogged. That's why the second dot is smaller. But we're talking about dimension about 40 nanometers for the first one, about 20 to 35 nanometers for the second one. The overlap is only about 100 square nanometers, and the capacitance in this case is about between 15 and 40 attofarads, which gives you very good operation at temperatures up to some 20 Kelvin. Now, this is the electrostatic map of what happens if you apply this differential bias. You can see that the field mostly propagates across this dipole, and there's a very little field which spreads across these detectors, because, of course, you don't want the detectors to react to this differential bias. And this is an example of what we measure. So basically, this is the response characteristic of our sensor. And on that scale, this is how much we detect. So this is the detection of the electron switching from one dot, the dipole, to the other. As you can see, the charge increment is fairly small. It's only about 1/100th of an electron, but it can be quite reliably detected. But I must show you, this is the average result. If you look at the raw data, it looks slightly different. So in this particular case, we did some 100 trace averages, and I'll give you this. You can kind of see even there that something's going was not very high signal-to-noise ratio, obviously. Now we can do it with two detectors, like I showed you in that picture. We have two detectors, and you can see that. And again, this is the raw data is black. The red data is our average signal, and on the other side, it's the alpha detector, which also gives you this sawtooth oscillation. And there's something else going on. Well, what is it? Well, in fact, what happens is we did, in this case, we detect about 0.03 electron. But what happens is, why do we see these two oscillations? Because each of these detectors can be perfectly tuned. Only one of them can be perfect, because you cannot afford perfect symmetry. At least maybe you can, but it will require very complicated fabrication. So we can tune one very nicely, and the other one will be charging, and so the blue one is charging. So this detector is not perfectly tuned, so it produces a bunch of oscillations, which we detect with the other detector. So we observe the dipole charging, and also we observe across the aisle charging of this other device, which is kind of nice, because you're making sure that you understand what's going on and within this little playground. Now, can we move them closer? Well, sure enough, we can do a little bit of changes in our lithography. So we'll have this close proximity, and now we have, see the difference between this and that. Oops. Yes. Okay. So we can get closer, and as a result, we can get, this is a structure which was fabricated. And as a result, we can get much nicer coupling, and therefore stronger signal. And at 2.7 Kelvin, this is actually, these are 200 traces of black dots. So they're not very well, it's not a huge spread, to be honest, right? The red curve is just beautiful and very nice and smooth, but still, even the raw data look very promising. So, and as a result, we can see that our sensitivity went up by almost factor, by almost an order of magnitude, and we get very good signal. This was actually what we published for this conference. So the temperature, as you can see, went up from below 100 millikelvin to 2.7 Kelvin. We investigated several ways to enhance sensitivity, and the application, it's not only for this mQCA, but again, think about mQCA, molecular QCA will require detection of dipoles on the order of nanometer. Of course, this technology cannot bring you there. It's just beyond the limits. But however, you can use it for fancy detection of this zero mode qubits, where you basically have a quantum dot, which is on the order of several hundred nanometers in diameter, but you need to place a bunch of electrometers there, and do some triangulation to figure out the position of this complex systems in that field. Another way we're also going, we're performing right now some experiments with radio frequency reflectometry, where you sense it with the gates. With that, I guess I want just to thank you for being here. And this is our campus, and it was supported by NSF grant. So if you have any questions, I'll be happy to answer.